This is the final week of fall term ESM 101, and today we're going to talk about scientific adaptive management. And at the end, I'll give a summary of the term. So, at the very beginning, we started talking about problem types, and one of the ones was a wicked problem. And to address these, we need a rigorous approach. And so, at the very beginning, we talked about things that science was good at and what politics is good at or regulations are good for, but really this idea of a wicked problem, we need an approach that's going to be systematic, include values, and include changing scientific knowledge. And when we have that, we're going to have to interweave that with environmental policy and governance in order to get those approaches to these wicked problems addressed. So the main topics I'm going to talk about today are that scientific adaptive management is a method or a tool. It's a very sophisticated tool and brings in many different aspects of what we've been talking about. And that we can use scientific adaptive management to address issues around sustainability. I'm not going to talk about this too much today, but it's related to the idea that sustainability is a very forward-looking, what's going to happen in the future, and because of the inherent uncertainty of the future, scientific adaptive management is very good for that. One thing we will address very clearly, I hope, is that thresholds are a big challenge, and a threshold is where a small change ends up in a small perturbation ends up in a big change in the system. And then finally, we'll come back to this point about how scientific adaptive management helps address the values and puts these science and policy issues into the realm of politics so we can find the resources to solve these problems. So the definition of scientific adaptive management is it has to do two things, and both of these are required. One, it has to help alleviate the problem that exists currently, and it has to reduce the uncertainty for future management. So it's not one or the other. It has to do both of those, and so therefore very high bar for the types of overall programs that can be called scientific adaptive management. So again, it's not simply trial and error. If you have a new problem and you try something and it doesn't work, that's trial and error. This is a very good way to find out about new problems. Try some solutions, see if it make any progress. But scientific adaptive management, you have to have a statement of management objectives stated as hypotheses. You have a program of manipulations where maybe depending on underlying models, you come up with, here's step one, and then depending on the results of that, you go to step two, you go to step three. Maybe it's a whole tree of possible manipulations you would use, but it's very laid out to address what happens if your management activity as activity as an experiment ends up on one path versus the other path. You do different things. And finally, it requires management activities, monitoring, and adaptation of all those that feedback. So let me give you an example. We've been talking about this through the term, which is managing the harvest from fisheries as scientific adaptive management. And this is really a good case because we don't know how many fish are in the ocean. And we could use research. We could go out there and have research boats trying to count fish. But instead, using the fishing effort, that is the management and harvesting approach itself, the amount of effort that the boats out there expend using scientific models to interpret that in terms of the population and the size of the fish, the population size and the health. And then with this management approach, you look at the return, that is how many fish came in and how big they were, estimate the population and the growth rate, and then adapt the fishing effort. So it's an adaptive management scheme that depends on the harvest. So this is a very good example of scientific adaptive management. So here's how it might look. There's underlying models for this fisheries that we've talked about before. There's the idea of carrying capacity up here at where the population levels off with time. There's we talked about the idea that in this steep portion is where you get the maximum harvest. If you can have the population at this level, you can get the maximum sustainable harvest in a very simplistic model, because that's where the growth rate of the population is the highest. And then down below a certain point, you have this minimum viable population. We talked about this, the Ali effect, that if it goes below this population, the population is a drop off. So for these models would say you need to stay above this minimum level. If you stay in this sort of population range, you'll get the maximum harvest. If it goes up too high, you're going to end up with slow growth, and you could bring the population back down to try to get higher harvest rates. This is an example of how these fisheries models would depend on underlying models. The fishery harvest would depend on underlying models that could be addressed scientifically by creating hypotheses and addressing those hypotheses. So most of these scientific adaptive management projects, and I can't think of any that don't, rely on models. That's because a model is a simplification and a representation of the real world. The model can be very simple or it can be very complicated. But one advantage, or a couple of advantages of these models, is that they're based on a specific set of assumptions that can be tested, and they make a prediction. And then that prediction becomes the hypothesis. So we talked about this exponential growth versus sigmoidal or logistic growth. The prediction for exponential just keeps going. The prediction for sigmoidal growth is that with time the population levels off. This is the type of what are the underlying assumptions? What would the prediction be? How can you turn that into a hypothesis? Now, just a little detour on scientific adaptive management is that there's really three underlying tenets of this. First, that all evidence, everything that's used is based on evidence and based on experimentalism. And what this means is you can't come in with preconceived notions or ideologies that don't depend on the specific evidence of the situation. So that's one requirement. The other is that you need to use multi-scalar analysis. Look at small parts of the system all the way up to large systems. This essentially makes you integrate across the whole ecosystem and the overall system, the overall context of the environmental problem. And the final is that it's place sensitive, and this goes back to emphasizing this experimentalism. Each place is unique, and you should start with the assumption that that place is unique, and that also humans are agents in the landscape, that they are part of the landscape and the system that we're studying. So these three together will really make some demands on scientific adaptive management. You can't come in with preconceived notions. You have to look at multiple scales and multiple perspectives, and you have to treat each place as potentially unique and deal with the human impact. So here's another example. This is the second of three examples here today. And this idea of lake eutrophication. And when lakes eutrophise, because the runoff from farms or erosion in nearby land leads to excess nutrients, that excess nutrients leads to the water that's too polluted with algae. So eutrophication means good growth, but really in the context of our human impact on lakes, it's usually too much growth. And you can see this picture down below. As the boat goes through the water, it's just this green. The whole lake is just filled with so much algae that it's really unusable for many purposes. Swimming, it's bad for fish. There's these huge blooms where the algae grows up very thick like this, and then when it crashes, it causes an oxygen deficit, kills fish, and really stinky, and isn't very useful for anything, for very many purposes. So that's the idea of this. The lake is polluted with algae, and the idea is that if there were lower algae, the water would be more valuable. So this is the value statement that comes in. If the water had much less algae, we could swim and recreate and use the water for other water purposes rather than, right now it's really only useful for farming. And so the hypothesis is reducing the phosphorus input would decrease the algae. And so, the models show that. And so the hypothesis is that lowering phosphorus loading will lead to less algae in a healthier lake. And by phosphorus loading, I mean the amount of phosphorus coming into the lake. So we have a sophisticated model to do this. I'm going to explain it just briefly, but it really has to do with sort of the excursion frequency. That's the percent of the time that there are blooms that exceed a certain amount of algae. And in this case, it's because the pH gets so high when there's a lot of algae, and it's very, very damaging. But that's a good proxy for these high algae conditions, which then are followed by crashes and death to fish and consumption of oxygen. So this idea of an excursion frequency is how many times, how many days, percent of the days is the pH greater than 9, or how many percent of the days is there like this really large algal blooms. And along the bottom axis is how much phosphorus is going to be reduced, how much the phosphorus is going to be reduced, the input of phosphorus. And this comes about by cleaning up streams, having better sewage treatment plant, better land use practices in general across the landscape in this lake basin. And let's just look at the red curve, because that's what the summertime, when we have the most extreme blooms. And if you reduce the phosphorus load by 20% from what it currently is, come up here, you go from 75% of the days having extreme algae to only 50%. So reduced by 20%, you reduce the number of days of bloom from 75 to 50%. But if you reduce it way out here to 40% of reduction, make a 40% reduction in the phosphorus coming into the lake, in the summer there's only about a 10% chance of bloom frequency. So this is the underlying model, and the idea is decreasing the phosphorus will decrease the percentage of days with these blooms, and also because of that will decrease the damage done by these algal blooms. So this is an underlying mathematical model that would be used to say, well, what's the desirable level? You don't need to go all the way out here. Is 10% frequency of blooms, is that okay? Can we live with that? Because as you get further and further out here, the cost more and more to reduce that next increment of phosphorus from coming into the lake. So again, this is an example of using that model, and then we made some predictions, and then generate some hypothesis from that, and that's what the management strategies are based on. Okay, now I'm going to give a third example, and we talked about this in the very first weeks of the class, this idea that Apple Island, remember in the South Pacific, there was poor fishing methods, that really meaning poisoning and blowing up reefs. So they created some marine reserves to replenish the stock, but when they did that, they hypothesized that there would be a tipping point, and that crossing that tipping point would put them across a beneficial threshold, and that they'd get bigger and bigger returns of fish. So actually the effort would be met with higher returns. And so this idea of a tipping point, ecological tipping point, is also the same as a threshold. And thresholds are very difficult to deal with, and often we're dealing the other way. Instead of a beneficial threshold, we're dealing with some sort of damage from an environmental impact. So here's, in the y-axis is the impact or negative response. Think of this maybe such as like toxicity of something. And here's what we have, the stress level. And if you increase the stress level, and for every time you increase the stress level, if you get the same sort of slope of the impact or negative response, that would be a linear response. It just follows along this line. But often we're dealing with thresholds, because down in this region we can increase the stress up to a certain point, but after that there's a big response, big negative impact. So this is what we call a threshold. And right in this region it's very critical. A slight change, instead of just continuing out at this low same slope, a slight change in the stress level results in a large negative impact. So we have to be very careful in these regions But the problem is we often don't know where the threshold is. There's a big amount of uncertainty. So again, scientific adaptive management would create a hypothesis about this, like that there is a threshold, and we have to be careful about it, and then design smaller scale experiments in management to try to test out where that is and avoid that. All right, so these are very solid scientific principles I've been laying out, but now how does this environmental science relate to politics? So just a couple quick definitions. The scientific approach requires objective statements, being able to independently verify that. Rigorous and transparent methodology, and by rigorous I don't mean hard, it just means well described, very tight methodologies. And then the point is to discover new knowledge and not just judgment about that. So the scientific approach requires that we develop new knowledge. Now politics is the governance of society, the distribution of power, and one of the aspects that's important for us in distribution of power is the distribution over the use of resources. There can be water, land, trees, fish, any of those things, but that is determined by these trade-offs that come up and are decided by by political governance. So, again, back to the first part of the class where we had these different types of problems. A simple problem where we know the answer, policy and politics are really, it's setting a policy and having the politics to people negotiate to find the resources to solve that problem. Common pool resource. Politics to reach an agreement, having what part of that society is governed by what institutions and what agreement can you reach. And information problems really just require more science, and then once they're better understood, they can be treated as simple problems or maybe even CPR. But the wicked problems, we need an adaptable scientific process that as we set hypotheses, so we continually generate new hypotheses, and we need resources to be identified and allocated to solve those problems. And again, this is difficult because people and governments and public institutions allocate resources based on the value proposition of what it's going to be to solve it. If the values are always changing as the information is changing, this becomes really sort of a crucial feedback to be able to show the importance of the science in order to get the money, use the money to keep generating new questions. Okay, now what's the role of environmental scientists in this? Let me just go back. One thing I needed to say about these wicked problems is it's very important that scientists don't overstate the role of science in solving the problem, because wicked problems aren't going to be solved. There's just going to be continual engagement with the problem. So that puts scientists in a sort of sticky role here. And what is that role? Well, first of all, I just want to make sure you understand that environmental action is not activism. There's a lot of actions that scientists take that are not activism. So we have this spectrum of involvement. And at one end is this objective scientific contributor, really taking no specific action relative to the environmental problem. Another level up from there might be the honest broker of alternatives, where the scientist describes different outcomes and how they can and compares them and does sort of a value judgment on that. Next level up might be consultancy. Environmental scientists are often environmental consultants. They work for an agency or a firm. They're involved in finding the problem and implementing it. One thing that Lee says, and he did a lot of work on the Columbia Basin, is that scientists need to be pragmatic about politics. That is where the money's going to come from, but stay idealistic about the science. Keep the science as pure as they can, but really get into it about these are the resources we're going to need in order to address these problems. Then there's scientists as involved stakeholders. There are many scientists that are actually personally, with their values and with their money and other things, involved in trying to solve the problem. And then they become involved stakeholder, but they still play this role as a science advisor or generating good science. And then finally there's the activist, and this is where this would be outside the realm of scientific adaptive management because it's belief driven. There's some ideology or underlying belief about what the right solution is, and that's really what's driving it. And we see this whole range. There's nothing wrong with being an activist if you really want to protect something, but there's not enough evidence for it, you might need to take the precautionary principle and really work hard because you believe it's important, and only later are you going to be able to prove that. So again, environmental science always gets knocked as being an activist science, but it's because there's all these different ways we can be involved, that is, environmental science and the public as citizen scientists. Okay. Two more points about these large environmental projects. One, they're a challenge for democracy, and a key part of that is that these are very complex environmental problems. Ecosystem restoration, dam removal, watershed restoration. These are huge projects. They require a large amount of information, and that information is complex. People need to be able to deal with thresholds and uncertainty, and as we described in class, people are very good at avoiding uncertainty. They will take efforts to avoid an uncertain outcome. And then just the wicked nature of this means you can't just study a point. You have to be continually involved, really, forever, because the problem's changing all the time. And it's also a challenge to public institutions. There's many different governments involved. For example, where I work in the Klamath Basin, there's tribal governments, counties, cities, state, federal governments, all sorts of different jurisdictions. And the public needs expert knowledge to weigh in, but how do they know? Are those scientists activists? Are they stating what they believe to be true? Are they stating stuff they can back up? It's a very fine line between proposing a solution and then just believing that solution is going to work. And another point is that these large projects are a challenge to democracy. That when you have a large project like this, there's a case for social justice, which is, do you protect the individual or do you follow the will of majority? There's two different aspects of modern democracy that are handled, and there's always a conflict between these two aspects. Another large challenge to democracy is technocracy, where the technical experts just take over running that resource. And they do that with the economy. We have the economy run by the Fed and other international organizations with very little democratic oversight. And we can see that in some sort of resource management too. So this is actually an anti-democratic solution, that is technocracy. It may be impossible to get the public knowledge levels up in order to support democracy, but we shouldn't delude ourselves to say giving the reins of control over to technocrats or bureaucrats is somehow democratic. And then finally, and this is one thing that worries me all the time, is that democracy may not work in resource stress situations. That is, when you really have a stress in the environment and the resources are depleted, people may just resort to sort of a fatalistic approach and protect their own communities and protect what's theirs and just give up on the democratic process. And this is one of the challenges that democracy faces in dealing with our large wealth and natural resources. So, not to be too down on this, but these are the challenges to democracy that really require more citizen science and more literate environmental science, more literacy in environmental science in the public. Okay, finally, just a quick summary of the term, just to show how all of this relates to scientific adaptive management. At the beginning, we started out with problem types. Then we created some models for natural resource growth and harvest. We took different ways to look at those issues using systems models and network models. And then we saw the central role of uncertainty and how that's because we're predicting the future. Then we talked a little bit about a range of management approaches that address the levels of knowledge and the control and values. And of those, we looked at optimization, but today we focused on one of the most powerful methods we have in environmental science, which is scientific adaptive management, and as it approaches these wicked problems. So thank you very much for your attention.